Start. Hello everyone, this is my report Mixed Semantics Guided Layered Bounded Reachability Analysis of Compositional Linear Hybrid Automata. I'm Yuming Wu from Nanjing University, China. In this report, I will first introduce the background of hybrid automata. Then I will introduce the mixed semantics guided layered method and the two path pruning-based optimizations. And I will show the evaluations of our framework on some benchmarks. Finally, I will conclude. The first part is the background. Hybrid systems are systems containing both discrete and continuous components. Nowadays, these systems have been widely applied in many safety-critical areas. For example, train control systems and implantable medical devices. System failure may cause severe damage to human life and property. Therefore, formal safety assurance is important and necessary to such systems. And model checking is such a method. Hybrid automata is a classical modeling language for hybrid systems. Hybrid automata consist of a finite state transition system and differential equations in each location. If all differential equations of an automaton are constant intervals, it is linear hybrid automaton. And LHA for short. This is an LHA describing the water heater. X is the temperature. The system switches between two locations to control the temperature within a suitable range. Reachability, that is judging whether a given state is reachable. It's a property of automata that is closely related to safety. The state of hybrid automata is a tuple v and x, where v is a location and x is the value of continuous variables. In hybrid automata, two kinds of transitions can be made. One is continuous, stay in a location for a certain time, and another one is discrete, take a jump on the graph. Classical reachability analysis methods and tools such as headache, favor, and SpaceX are usually based on over-approximation and geometric computation, but these methods are imprecise, sensitive to the number of continuous variables, and not granted to terminate. In recent years, bounded model checking has attracted lots of attention. It restricts model behavior within a finite bound to reduce the difficulty of problems. In other words, it searches for a potential behavior within case steps. Although PMC can't explore state spaces exhaustively, it surpasses classical model checking methods in the ability to find errors. Typical PMC methods for the reachability analysis of LHA encode the model behavior in the given bound into a set of SMT formulas, and then find out the weakness through SMT solving. However, the size of the corresponding SMT problems increases rapidly as the model scales and the bound grows. A middle bound will lead to a large SMT problem. So we need a method to control the complexity. For LHA with several components, we call them compositional linear hybrid automata, and CLHA for short. The model checking problem is even harder for CLHA than for a single LHA. Automata interact by granting the simultaneous occurrence of shared labels. For example, on the automata, the order of shared label B and the shared label E and F is the same. Here I will introduce two semantics for CLHA. The first is the step semantics. On the left is the Cartesian product of CLHA from the previous page. We have to traverse 12 different paths in the automata. On the right is the step semantics. It requires each component path to have the same length and to enable each shared label at the same position by adding stutter transitions. Stutter transitions is the transition which start from one location and then jump back to this starting location. It usually represents only one path in the Cartesian product for the step semantics. And it will be inefficient if we check through the step semantics. The second is the shallow semantics. It is on the right. It only requires that all automata have the same projection on the shared label sequence. No extra stutter transitions will be added. Without the help of stutter transition, It is hard to enumerate such paths because we need to count each shared label, so it is difficult to describe with propositional logic. But in this case, we just need to traverse only one path in the shallow semantics. It covers more paths in the Cartesian product. Comparing the two, it is easier to find the path through step semantics, while it is more efficient to check the path through shallow semantics. So our goal is to combine the best of both semantics. We propose a layered method to analyze the bounded reachability of compositional linear hybrid automata in a divide and conquer manner. As shown in the screen, the method is divided into two layers, the discrete layer and the continuous layer. It also mixes two different kinds of semantics in different layers. The step semantics for path enumeration in the discrete layer, and the shallow semantics for path checking in the continuous layer. The discrete layer reports the path to the continuous layer, and the continuous layer feeds back infeasible path segments. In the discrete layer, we enumerate candidate paths by a SAT solver, and we encode each of its solutions into a candidate compositional path in the step semantics. For each candidate path, if it is then checked to be infeasible in the continuous layer, we use it to refine the SAT formula set. The path enumeration process in the discrete layer doesn't stop until there is no candidate path, which means the SAT formula or the SAT problem becomes unsatisfiable. In the continuous layer, we check the feasibility of candidate paths. We first generalize a candidate compositional path in the shallow semantics. And then its feasibility checking problem is reduced to a linear programming problem and can be solved efficiently. If the LP problem is feasible, we obtain a witness that satisfies the reachability specification. Otherwise, we extract the reason for the infeasibility of this path. We then report this infeasible path segment back to the discrete layer. This is a compositional linear hybrid automata model of a nuclear reactor system. The member automata of the system include a controller and several control rods. They have several shared labels such as add and remove. The number of locations of this CLHA increases exponentially with the number of rods, bringing difficulties to model checking. I will take this system as an example to illustrate the process of our method. The first step is to traverse the graph structure of the CLHA to look for candidate paths that may reach the target location. The transition range graph and the interaction between automata will be encoded as propositional formula. The encoding ensures that all Boolean variables that represent the locations or transitions existing in the searched paths are true, and the others are false. We can get a true assignment of the problem by calling a SAT solver. The result can be decoded into a compositional path. This is the bounded graph structure encoding of an automata, including initial condition and the transition relation, excluding and target condition. The interaction of compositional linear hybrid automata shared labels can be encoded through step semantics or shallow semantics. An SMT-based encoding was proposed to enumerate paths in the shallow semantics. It counts each shared label and needs non-Boolean variables, but SMT solvers don't perform well when the scale of the problem is large. To make the path traversing efficient, we choose the encoding method based on the step semantics. The encoding guarantees that automata which have a specific shared label have to enable each shared label at the same position. By decoding the truth assignment, we could get a candidate step compositional path as shown in the screen. For a step compositional path, all of its labels are sorted in a total order. If we slightly change the order of any two labels, we will get a new candidate path. and we need to conduct verification for each new pass. However, for two labels belonging to different automata, their order doesn't matter unless they are both shared. For example, both paths on the screen are likely to be enumerated by the previous process. The pass below is obtained by swapping the position of transition recovery 1 and a stutter in the pass above. We can see both paths are shallowly consistent with each other. Their feasibility will be checked twice if we conduct verification through the step semantics, and while only once through the shallow semantics. Therefore, for all candidate step compositional paths, we generalize them into stutter-free paths under shallow semantics. By removing all stutters on the previous page, we can get such a path in shallow semantics. Due to the complexity of the linear hybrid automata, the feasibility verification problem of the candidate paths can be encoded into the feasibility problem of a linear constraint set on variables delta ij, lambda ijx, zeta ijx, and TLJ. Delta ij is the time spent in location Vij, and lambda ijx and zeta ijx are the value of x when the S automata reaches and leaves the location Vij. TLJ is the time when the label L occurs for the just time. If the encoded constraint set of a path rho is proved to be satisfiable, rho is a witness to satisfy the reachability specification. And this linear programming process ensures the soundness of this method in finding a valid witness. If rho is not feasible, we should prevent such a path from appearing again in the future traversal. We use the irreducible infeasible set method to locate the infeasible core path segments in rho and exclude all paths that contain such infeasible path segments. An irreducible infeasible set of an infeasible linear constraint set is an unsatisfiable set of constraints that becomes satisfiable if any constraint is removed. For example, ABC here is an IS and D is irrelevant. Mapping constraints in the IS back to the shallow compositional path, we can get the infeasible path segment represented by solid lines in the figure. In our method, we use the step semantics to enumerate candidate paths, and we obtain the infeasible path segments through the shallow semantics now. Thus, we need to map the infeasible path segments back to the form of step semantics for letter set refinement and encoding. And the dashed part in the figure is the path segment mapped back to the original path in step semantics. We refine the path enumerating problem by adding the negative encoding of the infeasible path segment back to the bounded graph structure. The refinement is as follows, where P is the position of the first location of the path segment, and K is the bound, L is the length of the path segment, and the infeasible path segment P is the negation of the conjunction of all variables that encode such a path segment when its first location is at P. But there is something unsatisfying here. Only the above one of the two similar paths just now will be blocked. Although the other one is also infeasible, our infeasible path segment is not working because the location of the stutter was different. To avoid such redundant paths, we propose an optimization. Paths that are identical to each other under the mixed semantics represent the same path in the shallow semantics. As we check the feasibility of paths through the shallow semantics, we hope to obtain only paths which are non-identical to each other. We summarize three classes of conditions in which identical paths are generated. Next, I will introduce these three cases by three paths. These three paths are identical to the one below. The first is global weighting. Start transitions could be inserted at any position endlessly to postpone other transitions. If all automata enable a starter transition at the same position, we call such condition global weighting. To avoid such redundant paths, we set up a new blocking rule. It requires that for any position in a compositional path, all member automata are not allowed to enable the stutter translation simultaneously. To satisfy this rule, the path should delete these stutters like this. The second is repeated waiting for shared labels. Similar to global waiting, simultaneous stutter translations before a shared label will also cause redundant paths. Since a stutter translation is inserted in a member automata, in order to ask it to wait for and synchronize with another automata on their shared label, there is no need to insert stutter translations simultaneously before one shared label in every related member automata. We call such conditions repeated waiting for shared labels. As shown in the figure, stutter translations appear before the shared label as 2. We set up the second blocking rule to avoid such redundant paths. It requires that for any shared label of CLHA, all member automata with this specific shared label are not allowed to enable the stutter translation simultaneously. To satisfy this rule, the path should delete these stutters too. The third is random waiting. As shown in the screen, a stutter translation may occur before a local label, recovery 1. We call such conditions random waiting. The purpose of stutter translations is to make shared label occur at the same position. Thus, member automata should only enable stutter translations to postpone a shared label when necessary. So we set up the third blocking rule. It requires that for each shared label, a stutter translation is allowed if and only if its next label is a shared label or a stutter. To satisfy this rule, the path should swap the position of the stutter and the local label recovery 1. Overall, our main idea for these 3 rules is that if a translation is selected, it should appear as early as possible in the path, rather than being delayed by stutter translations. Just like this path in the picture, we only enumerate and check such paths, and the path to be checked is the shortest of the identical paths. We have not missed any non-identical paths and will not generate an incorrect verification result. The second optimization method is multiple infeasible path segments-based pruning. As shown before, the IS acceleration technology is used to accelerate the path enumerating process. If we can find more infeasible path segments from one infeasible path, we can take advantage of more infeasible segments and block more infeasible paths. Therefore, we propose an acceleration technology that retrieves multiple IS by splitting the path based on shared labels. In the figure, different colors represent different shared labels. We try to repeatedly split the candidate path based on shared labels from its rear end. If the remaining shallow compositional path segment is infeasible, we extract the IS from the current linear constraint set and then continue to split the path. Otherwise, if the remaining shallow compositional path segment is feasible, stop splitting. By splitting paths in this way, we could get multiple infeasible path segments. Next, I will show the experimental results. We implemented the method into the bounded reachability checker BACH, and 6 well-known benchmarks of compositional linear hybrid automata, which cover all compositional linear hybrid automata cases in ArcComp 2020, are used in the experiments. In these benchmarks, DISC and TTE have only the unreachable version, while the other 4 cases have both reachable and unreachable versions. In the reachable version, there is at least one run that reaches the target state within a given bound, while in the unreachable version, there exists no such witness runs. We use the reachable version to evaluate how fast our method can locate the witness, and the unreachable version to evaluate its efficiency of searching the entire bounded state space. Our artifact has successfully passed the artifact evaluation process. In the experiments, we run both the basic layered version, marked as BACH, shown in the blue, and the optimized version, marked as BACH-opt, shown in red. We also run HiComp, a state-of-the-art tool for the bounded reachability verification of compositional linear hybrid automata. And to solve the same problem, to solve the same problems for comparison, shown in black.
Looks like we lost the speaker. Let's maybe wait a second for him to return. Okay, we are still waiting for the speaker to reappear on AirMeet. Maybe we can give it another minute and let's see. Looks like the speaker's having trouble to connect. Yeah, looks like the speaker has a non-star. No, there. Let's see.
Oh, sorry, I didn't get that. I didn't know that I have last. Oh, let's start.
I think you were around the. Yeah, if you just continue where you stopped, I think it was you were just about to discuss the experiments.
Oh, yes. Oh, thank you. And here?
Yeah, I think you were further ahead. Maybe just go to the part where you.
Oh, this.
Because we have to wrap up the session, so we should maybe get.
Oh, this. I will conclude that these are experimental results in reachable models. We can say that both BACH and BACH outperform HiCamp significantly in all cases in the aspects of scalability and efficiency. And in the unreachable models, BACH fails to scale up to some large problems because there is a trade-off between space and time in our basic method. On the other hand, the performance of BACH outperforms the basic BACH version significantly with the help of non-identical paths and multiple as BACH performs space effectively. Comparing BACH with HiCamp, we can say that BACH ties with HiCamp in the motorcycle and the DISC cases, while it dominates in all other cases. It shows that instead of solving the large verification problem as a whole, like HiCamp or layered method could solve the problem efficiently in a divide and conquer manner. This is a table of numbers of checked paths in unreachable models. We can say that the reduction ratio of paths of the number of paths reaches 90% in most models, showing the effectiveness of our path reduction optimization methods in state space pruning. Finally, to conclude, we presented a mixed semantics guided layered approach to perform bounded reachability analysis of compositional linear hybrid automata. Instead of encoding the complete bounded state space into one SMT problem as classical methods, we enumerate candidate paths in the step semantics in the discrete layer and then check the feasibility of candidate paths in the shallow semantics in the continuous layer. This approach has been implemented into a BMC checker for CLHA BACH, and we will put it on the website in a few days. The experimental data showed that with the help of our mixed semantics guided layered BMC approach, BACH outperforms state-of-the-art CLHA reachability verification tools on the aspects of efficiency and scalability substantially. That's all. Thank you for listening. I'm sorry for my last.
Thank you very much for the talk. I don't see questions in the Q&A tab. Are there any questions on site?
Yes, we do have an in-person question.
Great.
So, sorry, I got lost a bit on the high-level picture. So what's your definition for the bounded reachability analysis? Are you giving any bound on the number of reaching times for node, or just give the yes or no for reachability analysis, or it's just a high-level general bound for the performance?
Thanks for your question. We gave the bound for the path, and this is the bound for each benchmark, and the back count the discrete step for us as the bound. So we just check the reachability within the bound. That's my answer. Thank you.
So this bound is more like complexity bound. It's like the number of steps needed to do this analysis. It's like this.
Yes.
Okay. Thanks.
Any other questions in the room? I don't see any other questions here.
Okay, great. So let's thank the speaker again.
Thank you.
Thank you.